Morning to all of you. First of all, I would like to thank the organizer for these invitations. And I would like to thank Antonio as well, but he's not here today. Maybe I should mention that it's been quite a while that I was attending the conference, so I might get a little bit of nervous, so please pardon me for that. First of all, I would like to say that as you presented so well, I mean, really, thank you. You set the benchmark there. That makes me even nervous. And Kasha, thank you for the overview of the printed electronics. Yeah. So my name is Phoebe. I'm the general manager of Raynergy, a chemical company focused only on the proprietary organic semiconductor. So we do not do Me Too. So we only do our own IP patented material, and we focus on organic semiconductor. And today I would like to share with you some of the progresses that we have made in the NIR and the SWIR, shortwave IR optical material for the optical sensor applications. Right, here, first of all, I would like to show you a video in collaboration with National Yangming Jiao Tong University. This is an OPD incorporated on a glass substrate. We want to demonstrate the heart rates detected by the organic layer that we developed. So you can see that when benchmarked to the iWatch, somehow the number registered by the OPD is 77, is quite matching to the smartphones on the same persons. So we just want to show you that making the organic material, it actually works very well, and it with the correct methodology with the circuitries, so it should be able to commercialize, becoming a thin film and incorporated to smart wearable devices. Yeah. Okay. Next. So for the photodetector, or we call that as EMS sensor, commonly. So we can actually divide them by material. So the mainstream one in the market can be okay, let me see. Actually, I prefer to use this. Okay, there we go. All right. So the mainstream material is silicon, as we all know. It's everywhere from the display to the IC. So even in the CIS, CMOS image sensor. So silicon can absorb visible range from 400s up to 1100s. Then in the shortwave IR range is mainstream driven by the 3-5 group of semiconductor, indium gallium arsenides. And germanium is it's a wide spectrum material from the visible range to the shortwave IR. So, but germanium is very difficult to grow. So now people is using the germanium deposited on silicons to enhance the spectrum response of silicon up to near IR. There's some limitations to make this technology difficult for the shortwave IR, and I'm going to tell you in the next few slides. And why organic semiconductor is unique. So let's look at this very first one. The organic molecules look something like this. So when you connect a lot of molecule like this and it become a polymer, it can be dissolved in solvents and it can be printed. For P3HT is actually absorbed in between the 400 to 700s by manipulating or incorporating different functional group or change the conjugation length. You can actually switch, or you can actually lengthen the absorption or absorption spectral response from the visible range to close to the near IR. Then again, then you see we can slowly manipulating it to be close to 1200s. Then now in 2022, there's this Gasparini, they already demonstrated that organic molecule or semiconductor that can actually absorb at the near IR regions. So this actually make organic semiconductor unique because we can tune the spectral response. It's designable. Now, the potential organic semiconductor, like I mentioned just now, is designable spectrum response, tunable bandgap. So, and the second point that makes it very sexy for this application is that we have very good absorption coefficients. Comparing to silicon, it is at least 10 to 100 times higher. So, for sensor, what we need is not in the high light or very sharp light condition. It's actually at the ultra low light condition. And this make organic semiconductor semiconductor very, very attractive for these applications. And again, manufacturing-wise, organic semiconductor can use low temperature and it can be dissolved in solvent. It can be works like just like a photoresist coated on a wafer on a TFT. So it's a facile manufacturing and very fast throughputs. It's cost-effective for large area and earth-friendly material comparing to quantum dots, which still has some array of material. Perovskite also have a problem with the lead. So somehow organic semiconductor is quite of a leader in this selections, I would say. Now, let's look at the image sensor material technology competitiveness. Silicons is a mainstream and it's our yardstick. Now, but it could only respond in the visible range, but not to the SWIR spectrums, totally a no-go. Silicon, it's because it's well studied for more than 50 years, so the cost is well studied and well controlled, and toxicity-wise good. Manufacturing definitely no problems. But Indian gallium arsenide PD is used in the SWIR. It is very, very expensive. It can be a chip, could be go up to 10,000. More than 10,000 per chip. So it makes it very difficult to be commercialized, widely to be used in all the applications. So for the advanced technology for the image sensor, there are three material. Quantum dot is definitely one of them. Germanium silicons is driven by Artilux company also in Taiwan, and organic PD. Now, looking at all this, I would say figure of merits, OPD would show somehow a very good progress because we can actually meet most of the needs, right? So now organic PD and all organic image sensor, it's actually very acceptable to the market test. Why is it so? Because of the main driven by the AMOLEDs, it's successful demonstrated on TFT and micro OLEDs on the silicon. We have a compatible process. So in this OPD device, actually a basic diode devices where the material is sandwiched in between of two organic layer. One is a whole transport layer, another is electron transport layer, and sandwich between bottom and top electron. Obviously, it has to be transparent. Yeah, so we can incorporate this organic layer on the CMOS or the TFT as a readout IC. So for large area wise, for fingerprint sensors, as for example, we are using a TFT-based process, and for higher performance, usually the foundry will be the main customer and incorporating on the CMOS. So what we need to do is to change or replace this current silicon layer, PD layer, which is 3 microns, to a thin layer like the QD or the OPD layer. Right. I'm going to show you this picture. We have missed a lot of things in 2021 because of the pandemic, but you should not miss this. Panasonic has announced in this Tokyo one of the conference. So they have shown the demonstrated organic sensor with 35 MP, and this is a very nice picture where you can see a bright and dark session, and yet you still can capture very delicate and fine images of every single details of it. Why we can do so is because organic material somehow can realize the 120 dB simultaneous capture wide dynamic range, which makes the low and bright light conditions balance image conditions. So organic sensor, it's no longer only in the R&D phase, it's actually going into a commercial perspective now. Now, the opportunity of infrared sensor in what we have understood is that silicon, it's a mainstream for the visible range, like a camera, but they cannot enter the NIR-IR. So we think that the game changer for organic would definitely to be in somewhere where silicon cannot go to, which we think that is the infrared sensor. So for biometrics, for AR/VR sensor, and fingerprint on display, definitely one of that, because silicons using the CIS chip is very small. So on some of the phones that you use, they can only fingerprints on a specific area, not the blind verification, and so is the gaze detections. So for the near, as we go into the, so this region can be played by silicon. So we think that it is not easy to penetrate. So we focus on the material development for the NIR-IR to show wave IR. So the typical camera can see images like this because the visible range usually cannot detect very well under certain foggy conditions. But for machine vision and the SWIR camera, you can see the differences between the images. So that makes shortwave IR camera in eye needs. For the market-wise, we, as a material company, we forecasted that in 2027, there are 5 major applications that we are targeted. Number one, definitely the fingerprints, and I'll tell you why. Face ID to hide the camera or the IR sensor beneath the OLED display. Eye tracking for AR, VR, wearable optical arrest sensor for vital sign monitoring and assisting driving. So altogether, add up will be close to 400 million for the materials sales. Now, I want to highlight that for the OLED display, why that organic PD is in it. We all know that conventional, the front plane OLED made with a polarizer on top. Now, but with the folded phones currently in the market, they're actually replacing the C polarizer to the new technology called color filter on encapsulation, or COE, on OLED display. And because of this, there is actually black matrix incorporated in between of the RGB. And now with this new technology of the front planes, imagine you have a CIS chip lies beneath of the OLED display. When the OLEDs lights up and get reflected back because of the fingers, it gets blocked by the black matrix and makes the receiving lights very much lesser, and therefore the CIS may fail to sense under the COE OLED due to the reflected lights as being blocked. Hence, OPD sensor with 100 times better absorption coefficients will be one application solutions for the fingerprint on display under the COE OLED. Now, there's also emerging market opportunities such as palm sensing. I'm not sure whether you're aware that in Beijing, there is this demonstration show that people are using palm beam scanner for metro payment because you do not need to bring a phone or you do not bring your cards. So, and with this, there's one problem because silicon is very small, and due to the depth of focus, usually you have to place your hand at a certain distance from the sensor, which is difficult to gauge. So if we have a large area that can capture the finger palms easier, then that will make this application easier to be introduced. So OPD being able to do a large area, that will make it easier for the market's evaluations. This I do not need to speak much because most of the famous phones maker, they are always trying to hide the camera or the IR display, but still because of the CIS now is RGB in nature, there will be somehow have a interference effect to the front plane, and therefore they have to have a notch and make the camera or the IR sensor facing directly out. So we are making the SWIR sensor to make it possible to hide entirely under the OLED display. This, I must tell you also, the potential on OPD in a wearable optical sensor is massive. Take, for example, the PPG. Now, we all know that the wearable device will have these green lights because it's very cost effective and our body and bloods are responding very well to the green lights. But there's actually one problem that our skin, melanins, actually it's very good at absorbing the green lights, and therefore for color people like me, we actually the detectivity of the PPG using a smart wearable device is actually affected. You are not aware of this, but Garmin actually have shown this on their website and say that the skin tone can be affected by on the heart rate, and therefore they need to work extra hard. Therefore, your smart watch may consume more battery. So why this is a problem, because currently we are using a green light sensor. So in order to solve this problem, we may need to move this to the NIR-IR to the NIR-IR. But now also the other how to solve this is to increase the area of the sensing. So there's many papers studying about this now. There's this PPG over a large area using the OPD array types photodiode. So you may pay some attention to these developments. And this is no new news already, but in 2021, Samsung, they have already demonstrated organic sensor on their OLED stretchable display. And in Samsung Display Week 2023, Dr. Choi, the president of Samsung, they also has announced the all-in-one sensor OLEDs for new value creation. So they also have demonstrated OPD organic photodiode embedded in OLED display. Now, coming to Raynergy's tech material portfolio, what we have developed. We have 4 generations of the material so far. We have visible range, PD visible M and PD visible R. This is our starting point where we're trying to design a material that is stable enough. And this is for the TFT material for the TFT customer, for basically developed for the fingerprint on display. Then the second generation is the PD850. We have achieved an outstanding QE at 80%. What makes it more sexy is that we have RGB with a very flat curve and all registered at 80% of the QE. So this is also being used, evaluated for the palm imaging. Now, the PD940 is a product that we are very proud of. We have achieved QE of 60%. To our knowledge, this is the best result without any optical or modulations. And we believe that we are leading the developments on the SWIR, and I'm going to show you it next. So for the SWIR, it's basically providing to the CMOS player for basically the applications developed for the Face ID, mobile camera, and also biosensor. Now, speaking about the 940 material that we have, to the best of our knowledge, OmniVision technology 9cell2 series is the highest recorded QE and silicon-based CIS product for NIR sensing. This is the blue curve. This is the one, and they are registering at the 50%. Now, Raynergy's material, using the diodes stack, we are registering at close to 60% in this region. So we are without any more optical modulation yet. This 9cell is augmented using the micro lens technology. Initially, it was registered at 15. So you can see the difference. So we believe that we can achieve even higher, and the customer is developing for that now. Now, people may be wondering that is organic semiconductor robust enough to the semicons processors? So we ourselves as a material maker, we test it. And so we evaluate the photoactive layer patterning and process integrations. So what we did is that we have deposited the organic layer on glass, and then we put the conventional photoresist systems, protection layer, a photoresist layer, then we do a lithography process on it. After the stripping, we can get very nice patterning images. There's no problems. Now, the results, how it goes is that with comparing to our typical test kit, which is ITO glass material, the device, which is a black curve. Now on silicon test kit, after the litho and dry etching process, we can achieve similar and even better noise signal to noise ratio. And there's no hertz on the material at all. So basically you can see that the QE is still maintained at the 940 region. So this is something that we think the material is robust enough to go through the manufacturing process. And how about the temperature wise? So we have after we finish the device, we actually will do a post annealing of 120 degrees Celsius. You can see that before the post annealing annealing, we found that it is actually not quite stable. But after we do the post annealing after the entire stack is being built, we can actually turn to stable with QE register to 40% on the silicon, so which is go back to the normal, and it can actually sustain for more than 120 minutes. So we believe that the material is has good thermal stability over time. Now, regarding the progress in SWIR, and you may be curious now, can organic material be stable enough for such a small band gap? Yes, we can. We're slowly getting there. We start from zero early this year, so early last year. Now we are making progress to meet a customer target, which is QE at 30% and dark current at less than micron level. So now what we can do, what we can have is a T1 system where we register at -4 watts. It's with 31%, which is already achieved customer spec, but we still need some tweak to lower down the dark currents. And the T5 system show extremely good dark currents, but we're working on the QE. So we are blending these two systems now to make it work for the customer. So over these 2 years, the dark current is expected to be suppressed through the device interface engineering and carrier block layer. We have put all the efforts in the active layer, and then we sort of realized that the interfacial material is very, very crucial as well. So we'll now put on some efforts on that layer. So now we basically have tried to achieve increasing the detectivity 10 times per year. So we're starting from 2021 with close to only 5 or even 0% on the QE. Now in 2023, we are here. Basically, we can achieve close to 30% of the QE, and with dark current in these regions. Our target is here, and we are going to make it by September this year. So I think the material is already ready, and hopefully the test will go smooth. So, and regarding the 1300s, and we can also have a system called T6 now can absorb up to 1500s, which maybe can be used for the time of flight applications, which we're also very proud of that. So I think in when benchmark to Collier Metal Horizon 2022 findings on all the technology for the SWIR, I think organic material is actually rising up. I mean, in terms of the performance. So maybe I hope that you could pay some attention to this technology, and if you have some collaboration need on the material, please contact us. And this, I would like to show you our team from Taiwan. So we are a team of 28 persons, very driven scientists and very approachable. So we would like to extend our invitation to you. If you would like to test our material for any of the circuitry or PD, please let us know. So yeah, thank you for your attention for the talk. Thank you.